Everyone, welcome to CHEM. Now today's video is on group 13 chemistry, and here we are going to deal with monomeric BCl3 and dimeric LCl3, hydrolysis of aluminium CH3 and BCH3 and non-existence of borane, that is in the form of BH3, and tetra coordinated boron structure, as well as the boron chemistry. Now before starting, already 4 videos are uploaded in channel, you can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to CHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So the first question is that BCl3 is monomeric in nature while AlCl3 exists in dimeric form as Al2Cl6. Now first of all, you have to understand that in case of BCl3, what we see is there is a bonding between a boron and a chlorine, right? And this boron has a 2p orbital and this chlorine has a 3p orbital, and it forms a bond, as well as there occurs a back bonding from the chlorine. So the deficiency of boron is somewhat compensated by chlorine. Whereas in case of, if we consider AlCl3, then in that case we have a aluminium atom with a 3p orbital, right? And again a chlorine atom with a 3p orbital. And there is also a bonding, which is only a single bond formation. So there is no compensation of the deficiency present in aluminium, as a result of which it forms a dimer which is somewhat with the same atoms. So we have an aluminium, another aluminium, right? And a chlorine is attached in this side, whereas for this side, here are the 2 chlorines, right? One chlorine here, one chlorine here. As we can see that this chlorine bond present here has 2 electrons, right? Similarly, this chlorine has also 2 electrons. Here is a lone pair in the chlorine, as well as here is the lone pair in the chlorine. So this lone pair gets donated to aluminium and this lone pair gets donated to this aluminium. As a result of which, there is a formation of a banana bond. This is one bond in the dimer and another bond is in this part, that is starting from here, this part. So there is a formation of banana bond and there is an involvement of 3 center 4 electron, this one. So there is an involvement of 1, 2, 3, 4 electrons, and there is also involvement of 3 centers, 1 center chlorine, 2nd center aluminium and 3rd center also aluminium. So this is the main reason for the formation of dimer. So let us see. First of all, in BCl3, it is due to the smaller size of boron that it can participate in delocalized p-pi back bonding, which we had already seen in our previous video, with filled p-pi orbital of 3 adjacent chlorine. Thereby, it reduces its electron deficiency at the boron centers and hence stabilizes the molecule. Next is, such back bonding is not observed in case of AlCl3, as due to the large size of both aluminium and chlorine. Thus, in order to reduce this electron deficiency at aluminium center, 2 such monomeric AlCl3 units come close to each other and undergoes dimerization via forming 4 electron bonds. And it is due to the such mode of bonding that the electron deficiency at aluminium center is reduced. And also we have to understand that due to dimerization of AlCl3, coordination number is enhanced. The coordination number of aluminium enhanced, and this enhancement of coordination number is only favored if it has a larger size, so that it can accommodate more and more ligands, right? So this was the answer to this question. Next is among BCH3 and aluminium CH3, which will undergo hydrolysis faster. So first of all, if we try to draw the structure, this AlCH3 will be present in the form of a dimer. So it will be present like a dimer, just like the previous one. So this is our dimer, CH3, and here also CH3, and this joins. So if we try to hydrolyze, what will come first? Water molecule will come first, and this water molecule is highly acceptable. This aluminium always stays electron deficient how much bonding it goes along with, though there is dimer formation. So whenever this water is coming, it can easily accept these lone pairs towards itself. And since aluminium has a larger size, so it can expand its coordination number very easily during the transition state formation. So ultimately we can say that this particular AlCH3 can undergo hydrolysis more faster. So if you see here, AlCH3 will undergo the hydrolysis at a faster rate, and in this case there is a vacant 3D and it can accept electron density from nucleophile water, but this is not possible in case of boron in BMe3, whereas due to the large size of aluminium, it is able to expand its coordination number during transition state formation. Our next question is that BH3 does not exist but B2H6 exists. Now how is B2H6 formed? Let us see. B, again same, hydrogen, hydrogen and another hydrogen. Similarly here hydrogen, here also hydrogen, and here another hydrogen, right? Now if we try to see the bond formation, then one bond will be formed between this one and another bond will be formed between this one, this hydrogen and this, right? And these are 2 electron bond. Now where from the 2 electron comes? The 2 electron comes from this boron and hydrogen bonds present here. This is 1 and 2 electron. Similarly for this bond it is 1 and 2 electron, and the 3 centers are hydrogen center, boron center and another boron center, right? Now we will see the explanation. So in case of monomeric BH3, it is unstable due to the electron deficiency at boron center, as there is no back bonding, and in order to reduce this electron deficiency at boron centers, 2 such electron deficient BH3 units come close to each other and undergo dimerization via the formation of 3 electron BHB bonds. Without the dimerization, it could not exist as there is high electron deficiency. Next we come to our next question, that is tetra coordinated boron compounds are always tetrahedral and never square planar. Now if we focus for the approach of the ligands towards this boron from square planar way. So if this is the ligand, it will try to come in this angle. Similarly for another ligand, it will come in this direction. So ultimately for square planar, the degree of approach is 90 degree, right? And if we consider for tetrahedral, so this is our boron and it will be approached from this side as well as from this side, right? So the degree of approach comes to be as 109.5 degree. This is tetrahedral. Now remember, boron is very small in size. So if the approach is in 90 degree, then there will be more steric repulsion, right? But in case of 109.5 degree, the steric repulsion is somewhat decreased as the angle of approach is increased. Also in case of square planar, it assumes a sp2 hybridization. for square planar it needs to have a dsp2 hybridization, whereas for tetrahedral it needs to have a sp3 hybridization. And we know that boron lacks d orbital, that is energetically accessible 3d, as a result of which we cannot observe any square planar geometry in this case. So let us see the answer, right? Due to the small size of boron, such approach at 90 degree will be steric repulsion at the bonding distance. Thus, square planar geometry is not favored. Whereas, if the angle of approach is 109.5 degree, such steric repulsion at bonding distances will be absent and hence the tetrahedral coordination is favored. Also, if we consider boron to assume a square planar geometry, then it will undergo dsp2 hybridization, but this is not possible as we know that boron lacks energetically inaccessible 3d. Similarly, if we consider for tetrahedral geometry, sp3 hybridization is possible and thus it favors the tetrahedral geometry. Last, we will come across boron chemistry. Now, what is this all about? This is a reaction involving boron and its different compounds. And here there is a flow chart which will be helpful for you to remember all the reactions. So, this is the flow chart. We will start from B2H6. This is a boron, diboron, right? So, first we will react diboron with water to produce BOH3. Next, we will add to it NH4HF2 to produce NH4BF4. Next, on NH4BF4 we will add B2O3 and heat. It will produce us BF3. Next, BF3 can be returned back to BOH3 by reacting it with water. This BOH3 can directly be converted to BF3 using HF, and this BF3 on being added with HF produces HBF4. Next, we come from B2H6. If we react it with ammonia at minus 120 degrees Celsius, this complex is being formed, that is BH2NH3 whole 2 plus BH4 minus. Next, if we react it by heating, then there is a formation of borazine, B3N3H6. As you know already, borazine is being covered in the inorganic polymer chapter. You can watch the video. I will give the link in the description box as well as the I button present above this video. Next, from B3N3H3Cl3 on reduction using NaBH4 we can produce borazine. This particular conversion from this side to this side is already being shown in inorganic polymer video. You can watch it. I will give the link in the description box. Next, if we add BCl3 along with NH4Cl and toluene, again we can obtain B3N3H3Cl3 and from there we can approach borazine. Next, if BCl3 is reacted with water, we get BOH3. And if BCl3 is reacted with MEOH, that is methanol, then it produces BOMe3. Next, if we react BCl3 with ammonia and fuse, then we obtain boron nitride. And if B2H6 is being reacted with ROH, that is any kind of alcohol, we get BOR3. Next, we come across B2H6 on reaction with Me2PH and heat, it forms a sigma skeleton like this. And on reaction with carbon monoxide, it produces COBH3. Next comes, if we try to get back B2H6 from BF3, we have to react it with NaBH4, ether or LaH. From BOH3, we can obtain HBO2 just by heating, and ultimately on fusing we get B2O3. Now another one left is this one, that is if we want to B2H6 from BCl3, then we have to add lithium aluminium hydride. Okay, so this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.